Well, good afternoon, everybody. This is Gene Bohensky with IR Thermal Systems. The title of this presentation today is How to Choose the Right Heating Solution to Control Process Evaporation. This is a special presentation that's really going through all of our special technology and processes that we use to configure process heating solutions for our customer applications. And we're going to be joined later by our process heating expert, Jason Allington, who will really go into some of the details on some of the technology and techniques we use. But let's first get started with an introduction to our company. So IR Thermal Systems was founded in 2020 after the former management team purchased the assets and intellectual property of Radiant Energy Systems and Anderson Thermal Devices. The management team and employee experience dates from 1985, so we have a wealth of experience in the business. Our core competence is to design and manufacture custom engineered process heating solutions for improving process performance and lowering production costs. We focus on quality and dependability, constant investment in the latest manufacturing technology. We produce our own quality component parts, including stem foil heaters. We focus on continuous heating processes, and we're also technology independent, and that allows us the freedom to choose the best technology for the customer's application, whether it's a hot air solution or an infrared solution. So we basically develop large custom process heating solutions, like the one shown there on the right, where we do preheating, drying, and curing applications. We do hot air systems and combination hot air systems and infrared, where we use infrared to improve performance and productivity. So the industries we serve include converting, paper, film, and foil, printing, nonwovens, plastic, adhesive lamination, batteries, medical devices, filter media, fiberglass, advanced composites, industrial fabrics, automotive, packaging, wire and cable, textiles, and many other industries that use process heating. So how we work with your team. We have a specialized sales and engineering team that first reviews your existing process, and we determine the best technology to use for your goals. With state-of-the-art design tools, we develop a system tailored to meet your target specifications. We also offer lab testing services and our exclusive low-cost infrared rental program that allows you to try our technology in your plant. And we also have special project specification sheets, and this kind of shows you the kind of detail that we require from our customers in order to get started on the project. As each project is custom, we want to know your coating types, any special considerations you have for the process limitations, or clean or cleanliness requirements, as well as many others shown there on the list. And we cover two basic major applications. So the first one is drying, solvent vaporization, and evaporation, and that's what we're going to be focusing on in this presentation. Our other is just heating, where we raise the temperature of the product to cure, heat set, or treat the web to do polymerization or annealing. But this presentation is concentrating on solvent vaporization and evaporation. And to that aim, we can show this curve on a typical drying application, where you have on the y-axis dryer operating temperature and time on the x-axis that shows that you have a portion of that dryer time, which is used to heat up your web. Then you have your constant rate drying phase, and then your finished drying, where you get the temperature up to its final temperature and finish the drying. So the type of ovens that we specialize in that cover these applications include convection hot air systems. We have impingement drying systems where we use nozzles or ducts, and flotation drying where the web floats in the process. We also have combination infrared and hot air systems, which use infrared to assist or improve the performance of traditional hot air drying systems. Each technology has their advantages and disadvantages, and since we are technology independent, we are free to choose which is best for your application. So let's start with a little bit of information over impingement dryers, those that use nozzles. You can see there that air is blown through a nozzle to heat one or both sides of the web. This is used for coated and non-permeable webs such as adhesive tapes, protective films, coated fabrics, architectural fabrics, and other printed materials. It can easily be arranged for multiple heat transfer zones and adapted to different product requirements, and it offers accurate and uniform control of the dryer temperature. And you can see there on that diagram how the air comes into the nozzles and forces it onto the substrate. You have a turbulent air layer at the surface and a laminar layer directly at the surface. So a turbulent air just above that. And the coating can be solids or solvent, solids and solvent. And here is the other type, which is a flotation dryer. This is flotation dryers are direct, where you use direct heated air at the product from both sides, producing more effective heat transfer rates per running length of the dryer. This is used where the web is coated on both sides and for delicate webs that can't be mechanically supported or touched, including filter media and coated film. Non-contact web support eliminates issues with marking or scratching and eliminates the need for support rolls or a conveyor system. And this also offers accurate and uniform control of dryer temperatures and ease of multi-zone operation. And here you can see a diagram of how flotation dryers work. We use the Coanda radius effect that yields nozzle-to-nozzle tension components, and pressure pads at the nozzles develop controllable sine wave web path, and the web tension altogether allows you to have this web float through the oven or the dryer. And at this point, I want to turn over the presentation to our expert, Jason Allington, who will go through more of the details on how these dryers are configured to control process operation, evaporation.
Good afternoon, everyone. My name is Jason Allington. I'm the Vice President of Sales, and I've been involved in process air heating industry for about the last 18 years. So I'm going to go over the air delivery methods that we commonly use, and I'm going to go from a low efficiency zone to a high efficiency zone in that kind of order and work our way up. So the first type of zone is a quiescent zone or hot box, and it's one of the most basic types. And this type of zone has little to no impingement drying, and it is very quiet and has a little bit of very little heat transfer. It's often used to control the reaction on a web. The airflow in and out of the zone is controlled to maintain a specific set of conditions, mainly temperature, velocity, and humidity. It's got very low velocities of around 1,000 feet per minute. Some of these the applications that it's used for is for endothermic reactions, where a reaction on or within a web is giving off heat. This is seen in filter media often, and we're just looking to control the reaction and maintain it for a specific amount of time. It's also seen in wet bond laminates, where a coating between two webs or sheets is performing that reaction. The next step up from there would be a co-flow or counterflow zone. This can be controlled by a zone where you're delivering air on one side and taking it out on the other, or on an air bar to air bar basis, which is shown in the picture in the middle to the right. This type of zone has low impingement, and the nozzles can be close or far from the web. The nozzles or ducts direct the air mostly in the parallel plane of the web, and the web direction is independent of the airflow direction. Common air velocities for this are from 1 to 4,000 feet per minute. Because of the gentle nature of this type of zone, is often used for highly volatile solvents where the product could be subject to surface defects if drying happens too fast. So the counterflow or co-flow zones limits the evaporation rate of those volatiles. This is seen with thicker PSAs and battery lines, which are just two very common lines where surface defects occur, where you get fisheyes, bubbles, scratches, and occurring from retained solvent. One of the most common types of dryers out there is the classic impingement dryer, and this utilizes hole bars or slot nozzles. The hole bars have a series of non-lined up holes. They're in a pattern so they don't cause streaking, whereas a slot nozzle has one or two slots that direct a jet of air across the entire width of the web direction. So these classic impingement dryers, where the air is directed perpendicular to the web, the nozzles are set up so that they can be moved close or far from the web, depending on how intense you want the impingement. And the web direction is independent of the nozzle orientation. Common web or air velocities for this types of systems are 3 to 7,000, but we're not limited to that. Like I said, this is pretty much a standard type of dryer, so it can be used for both volatile or aqueous solids or aqueous coatings. You'll see these on toll coaters because they're required to run different products from across the converting industry. They're very versatile for general product selection, and the impingement nozzles are used when you want high or low velocity, but specifically directed perpendicular to the surface of the web. The next step up would be a single-sided flotation. Now, single-sided flotation can be located on the backside of the web, which you'll see it on the right middle picture. It's on the bottom side. It can also be on the other side since it operates like an airplane wing and actually sucks the web to it. The single-sided flotation nozzle or airfoil directs the air mostly parallel to the side of the web, which provides some energy input into it. It is a non-contact web support, so that carries the web through, that applies backside heating to drive out the solvent from the back, and you can select a variety of opposing nozzles. So that's what gives you the ability to adjust that energy input from very little to very high with this type of system, is selecting the correct nozzle that's on the opposite side. The air velocities are commonly but not limited to 4 to 10,000 feet per minute. The common uses for this type of nozzle would be on thicker aqueous coatings, medium to thick PSAs, and where no surface contact is required for product quality. That might be an optical film application or a very special tape. And since it is a non-contact web support, it can be used on double-sided coatings or on coatings where you have a backside adhesive that's been previously dried and you're rerunning the web with a new coating on the opposite side. Whereas if you put that over a roller, it may get stuck on that roller or have transfer of adhesive coating onto that roller. The double-sided flotation nozzle or Coanda nozzle has been around since the 80s, and it is a very standard nozzle for high energy input. The air is directed mainly towards the plane of the web, and it is a double-sided non-contact web support. Has a very stable flotation characteristics with this type of bar. The web direction, again, is independent of the nozzle orientation, and it has very high energy input into the Weber coating. The air velocities, once again, are pretty much the same as the airfoil from 4,000 to 10,000 feet per minute. This is most often used for double-sided coatings, very thick, heavy aqueous coatings, or heavy saturated webs. You can also be used for thinner volatile coatings that have high boilers, that you're not worried about them flashing off because it does have a very high energy input. You'll see this on this type of nozzle used on insulation layers for circuitry, where you're trying to drive off every last little bit of solvent within a thin coating. Now, along with all of those other types of nozzles, we can incorporate the use of IR heating. Now, they can be located, the IR heating emitters can be located opposing to or in between nozzles, and they are considered an independent zone since you can adjust either the intensity of the IR or the air temperature and velocity independently of one another. The wavelength on the IR can be selected to hit in a specific target energy input, and when this is in combination with the standard convection heating, it provides you the highest energy input into a Weber coating. The incorporation of IR heating into a traditional convection dryer allows you several things like it improves the energy efficiency of the overall drying system. It works really well with heavy saturated webs, high-speed applications, or systems where you are required to have a very small footprint. So where energy input into the web, high energy input into the web is of the utmost importance. We also use it as preheaters or post heaters for boosters, which allows you to run faster, increase your line speed, which expands your production capacity. And it can also be zoned across the web to improve the overall temperature consistency of your web leaving the drying systems. Now, this is just a quick reference graph of some of the most common applications. I've made this up to kind of as a speaking point years ago. Every year I do jobs that kind of deviate from this, but in general, this works pretty well when I'm looking at a new incoming system with a water-based silicone or a water-based adhesive, and I can use this as a talking point to help narrow down with a specific customer's process engineers. They might have want to look at what all the different types of coatings they have and how best are we going to design a single system to run all of those coatings. That's where it gets difficult, where you're trying to get multiple types of systems to fit in together.
Well, thanks, Jason. That was great. I want to finish out the presentation with just some pictures of some of the dryer systems that we've developed over the years. This one here on the screen is drying a solvent-based coating process in a tandem coating line at 1,200 feet per minute. Here's a conveyorized hot air impingement oven for heat setting fabrics. This one is a clean room infrared and hot air flotation dryer for curing silicone coatings. So another one of our combo dryers, curing systems. Here's a 20-foot long flotation and 20-foot long impingement dryer for manufacturing filtration media. Here's a 140-foot long 4-zone hot air impingement dryer for drying and curing solvent-based PSAs. And here's a 60-foot 3-zone flotation dryer with planar retraction for curing 100% solids silicone coatings at 1,000 feet per minute. And here's another flotation dryer. This is a clean room, stainless steel construction for flexible solar panels. And here's another nice picture of a infrared hot air impingement combo dryer for drying and curing coatings on non-wovens. So thank you all for attending our webinar.